Okay. So, before we jump in to doing the perpendicular bisectors of a triangle, let's just do the perpendicular bisector of a segment. Okay, so we're just going to do like a segment here. That's it. Okay, so like back to our original construction that we knew how to do. So on our papers, let's go ahead and just draw a segment. Okay, so I'm going to draw a segment like right here. Draw as long as you want, I guess. Don't go too crazy. You might run out of space. Okay, and let's call this segment AB. Okay. No, not really. Don't go too crazy though. Okay, now recall. Right, so let's think about this. All right, a perpendicular bisector. It's two words. What does the word perpendicular mean? If two things are perpendicular, what does that mean about them?
They make 180 degrees. Aren't they opposite?
Yeah, they meet in what kind of way, though? Yeah, at right angles, right? They meet at right angles. The slopes, yeah, so Debbie, I think what you were getting at there, what about the slopes of two perpendicular lines, for example? The slopes are what? Opposite and reciprocal, right? You flip them, too, okay? Opposite reciprocals. We're not in the coordinate plane right here, so we don't have to worry about, like, calculating the slope of this and then find the opposite reciprocal or anything like that. That's not necessary because we're not in the coordinate plane, right? If we were on graph paper, might be a different story. But here we just want to find the perpendicular bisector. So we want to come up with another line or another segment that makes a right angle with this segment. And what's the word bisector mean? Yeah, it cuts it into two equal parts, or splits in the middle, or cuts it in half. Okay, so we want a segment that not only goes through this at a right angle, right, intersects us at a right angle, but also cuts this thing into two equal parts. Okay, remember we use our compass for that. Okay, does anyone remember how do we place our compass to do this kind of construction? Alex?
Okay, don't you put the point on? Don't you put the point at like the A?
Okay, put a compass point on A, and then is my compass adjusted okay? Do I need to like open it any certain?
No, you should not touch it yet, and then you swipe up and down.
Right. It needs to be more than halfway though, right? So it is more than halfway, very clearly more than halfway here, and so yes, we can then swipe. Okay. Like so. Okay, give yourself a nice big arc there. Yeah.
Can't you just find the length of it with the ruler?
If you want to do it that way, Corey, I'm okay with that. Yes. And then what else? Are we done? What else do we still have to do here? Yeah, without adjusting your compass, without adjusting it, point on B. Okay, and then big old swipe there. Okay, and we create that little football shape. And yes, you need both the intersection point up here and the intersection point down here. Okay, if you don't have two crisscrosses like this, if you don't have two X's, you need to extend. You need to extend your arcs.
Why don't we do it in one thing touching the other?
Say again?
Like I did it halfway on.
Okay, so again, just do the big arc, and you need to extend that. Make that longer. Go back to A and make it longer. Okay, like make your arc longer. Okay? Alright, and so there we have the two X's right there, right? And we are going to join those two X's. So this point right here where they crisscross, this point where they crisscross, we're going to join those two things together. Right. Okay? Now, this is a right angle. Okay, right? And don't forget, and we can call this point, we call it C or M, whatever you want to say there. Okay, and then those are congruent. Right? AC and CB are congruent. Okay? You can call those other points, you can name those other points if you want to. You don't need to, though. They're just part of the construction. So I like to call this C because then we have, like, AC, we can say is congruent to CB, for example. Right? We can say that angle, the angle there is 90 degrees. So that means all four of these angles are actually 90 degrees then. Okay? Okay, so that was the perpendicular bisector. Hopefully that's just like a refresher kind of deal there. All right, but now let's draw a triangle. Okay, and I'm going to draw a kind of acute triangle here. So I would suggest you draw an acute triangle. Okay, draw an acute triangle. Well, that's okay. But you use a straight edge, and then it'll help it be pretty. Okay. There's my acute triangle. All right, let's name this triangle EFG. Okay.
So we make another triangle.
Have some trouble there with that. Okay. So yes, draw a triangle. Draw an actual triangle here now. Okay. EFG. Okay. Now, what we're going to do now, all right, is use this same construction, right? What did we do? We took a segment, AB, and we did the perpendicular bisector for that segment. Well, how many segments does a triangle have? 3, right? Okay, so we're going to do 3 perpendicular bisectors for this triangle. Okay, so let me show you that. So let's pick a side. I'm going to pick GF here. Okay, because of it's kind of like the bottom of the triangle. Okay, it's like facing me kind of thing. It's like, you know. So what we'll do then is do the same kind of construction that Alex was talking about. If you need to adjust your compass, don't forget you can like tighten the screw, right, by just turning the little knob there. You can go the other direction to open it up some. Okay, it's up to you how you want to adjust it. I'm going to adjust mine just a little bit. Okay, so I'm more than halfway. All right, and then we'll swipe, right, from point G. And then we'll do the same thing here at F. Point down and swipe. And that creates the perpendicular bisector of side GF. Yeah, be careful, guys. Like I said, it's not a bad idea to put this on your book underneath of it or something like that, because it will go right through your paper. It's very sharp, which will help it grip better, but also make it move around. Okay, so again, football construction, draw the perpendicular bisector.
So do we do it for like any other ones?
We're gonna get to that. Okay. If you want to, you can also erase back some of the marks. Okay, if you're like concerned about being neat, or if it's going to be too much for you, can erase back some of the marks. If it's just too much marks in your paper there. Okay, then we're going to turn our triangle here, and I want to turn it so that EF is now kind of facing me. Okay, and so we have another side here we're going to bisect, do a perpendicular bisector for. So let's do that. Okay, so EF. Okay, put your compass point on F, and I would suggest adjusting your compass. Okay, so you might be tempted to just use the same exact marking, like, because, you know, it's like, okay, there's point F, and, you know, my compass, I didn't really move it that much. Actually, I did move it a little bit there, but, you know, you might be tempted to just use the same distance you did for G and F, and you can. Like, it's not wrong to do that. However, I'm going to recommend that you adjust your compass a different length, and that way you don't get confused with these other markings, because sometimes they can like overlap somewhat. So again, compass point down on F. Okay, big swipe, and then compass point down on E, and a big swipe.
Wait, where are we starting from?
So what are we bisecting? We're bisecting FE, perpendicular bisector of FE. So you want to put your point on F, do a swipe, then do your point on E, and do a big swipe. And again, you should have 2 intersection points there. Okay, just like this. Okay, perpendicular bisector. If you messed up, guess what? It's pencil, so you can erase it and fix it, okay? So, compass point. Okay, and then draw that. Perpendicular bisector. Okay, question? Yeah, if you want to come up. Oh, there you go. Okay. So now we've got 2 perpendicular bisectors, and they intersect. Okay, no big deal there, right? Kind of makes sense that they should intersect. Again, if you want to erase back some of your markings, that's fine.
Can I get one of the old compasses?
There, you can take a look up front there. There's some left, I think. Okay? And then we have one more side to do. So now turn your paper a third time here. Rotate, right? So you get to GE. And it's not necessary to turn your paper too. I mean, if you want to keep your paper facing you the entire time and then just do your constructions that way, that's one way to do it. I like it. I think it's easier if you turn your paper though and just have it facing you. I think it makes it easier to do the constructions.
So do we all make it a different size?
Yep. So again, I would suggest adjusting it. So again, compass point on E, and I would suggest adjusting it, just a little bit different. Okay, again, swipe around E there. Okay, swipe around point G. Okay. And I did just an okay job here, I can see. And then again, draw your perpendicular bisector. Question? That's right. Okay. So now, when two lines intersect, that's not that special, right? You guys have seen two lines intersect here. But what does it look like is happening to all three lines here? They all intersect, and they intersect at the same point. They all seem to intersect at this one point right here. Now that's more special. To have two lines intersect at a certain point, that's no big deal, of course. Two lines, they can intersect, no big deal. But when you have three lines, and they all intersect at one point, well, that's kind of different, okay? Any two lines can intersect, but when you have a third line intersect at the exact same point, that seems to be a little more special, all right? And so, yeah, this is what we might call the center of a triangle, okay? But it's not just any old center, though.
The center.
Well, we call it a different kind of name. It's called the circumcenter.
Oh, that's what that is.
Okay, the circumcenter.
Oh, yeah.
Okay, the prefix circum means to go around. All right, and then center. Well, it's a center there. So where's the going around part? Why is that named this way? Well, because if you accurately draw your circumcenter, if you take your compass here and place the point of your compass in the center of the circumcenter, and then you adjust your compass, open it up so that it touches one of your vertices of your triangle. So for example here, I'm putting my compass point on the circumcenter, and I adjusted my compass so that it goes right through point G. Alright, so again, point of the compass at the circumcenter, open your compass up to G, and watch what happens here. Okay, and again, if you want, you can adjust, you can turn your paper and kind of turn your compass too. I'm kind of doing both. And what does my circle do?
Circle around
It hits all the points. It intersects all 3 points of the triangle. Okay? It intersects all 3 points of the triangle. Alright, I'm going to call this point, let's see, we'll call this point H. Okay? So, H is the center of a circle that goes around the outside of the triangle, that just fits that triangle inside the circle there. Alright? If I were to measure EH from E to H, how would that compare from G to H? So if I were to measure from E to H and compare that with G to H, how would that compare? It would be the same distance. Why?
The center of the circle, but it's also the center of the triangle.
Right, okay, so it's the center of the circle here. Okay, H is the center of the circle. If E and G and F are all on that circle, well, if H is the center, that means the distance from H to E is going to be the same as the H to G distance as the H to F distance. What do you call that distance from the center of the circle to a point on the circle? Yeah, it's a radius, okay? So EH is a radius, GH is a radius, HF is a radius. So EH, GH, okay, and HF, or FH, okay, are radii, okay? It's the plural of radiuses, right? Or plural of radius is radii, are radii of the circle, okay? So EH equals GH equals FH. They're all the same length. Okay. Right? Because of the way that circle we can draw, H is equal distance to E, to G, and to F. And so we can say the circumcenter, which is H, point H, the circumcenter is the point, okay, that is equidistant, right, equidistant from, and what's the geometric term we use for the points of a triangle? What do we call E, G, or F? We don't call them points, that's not mathematical, right? What do you call the pointy part here? Okay, angles, what's the pointy part of an angle called? Starts with a V. Vertex, or in this case for the plural, it's from the vertices. Very good, from the vertices of the triangle. Okay, from the vertices of the triangle. Okay. And so there it is. Find the center. Yeah, I don't know. Say again?
You know how we did it, we broke the nodes, set nodes, and then and then we just
Perpendicular bisector?
Yeah, exactly. Is this the same thing as that? No.
It's like continuing on from that, because what did we do? Here, we did the perpendicular bisector of a single segment. Here, we did 3 perpendicular bisectors, one for each of the 3 segments of our triangle here. You see what I'm saying there, Alex? So we took one perpendicular bisector, just kind of remind ourselves how to do a perpendicular bisector, and then we did 3 perpendicular bisectors to all of the sides, one for each side. We did a perpendicular bisector, the football construction. Okay? And those 3 perpendicular bisectors, 1, 2, 3, right? This is the perpendicular bisector for GF. This is the perpendicular bisector for EF. And then this right here is the perpendicular bisector of GE. All 3 of those perpendicular bisectors meet at a single point called the circumcenter. Okay? If yours didn't meet at a single point, then just try to be more careful with how you do your constructions. Okay? It's, you know, the more accurate you are, the better they'll line up. Good question. So, like, what kind of question? So, for example, if I were to give you like a map of the United States, for example, okay, and I, you know, there's like, let's say like we want to place a new airport. And we want that airport to be able to like be accessible between different cities. So I say, all right, here's 3 cities. Find the point between those 3 cities where that airport would be the, you know, equal distance to all 3. We don't want to like we don't want to build the airport closer to one city than other cities because we want everyone to be able to kind of access it equally. And so when you use something like this, you could imagine like E, F, and G would be like 3 different cities on the map, and then the location of the airport where it would be equal distance to those 3 cities would be H. You use like the perpendicular bisectors there to help you find where it's equal distance from those 3 points. That's one we could apply it. So you would draw a triangle between the 3 cities. You would draw perpendicular bisectors, and that would find roughly where you want to put the airport, somewhere right in there. And of course, you know, you have to worry about roads and things too. But I mean, that's the idea there, though.
You mean, is that
Say again?
that didn't happen, right, though?
What do you mean?
Go to every city.
3 cities, absolutely. We just did it.
3 cities, yeah.
3 cities, yeah. And you, of course, right. If you have like every city, well, that would be more difficult. But I mean, if you have like 3 major cities nearby. So for example, we have an airport, BWI, it's for Baltimore, Washington International. So the idea is they kind of built that airport kind of between Baltimore and Washington, even though it's closer to Baltimore, but they kind of built it between Baltimore and Washington so it would serve both of those big cities. Okay?
So to improve it, would be useful to use
So the idea is that since we drew perpendicular bisectors, we know that this point is going to be equal distance from G, F, and E. That's how we know it's true.
That would be given, right?
It would be like a given information, yeah. Once you have it constructed and drawn, yes. The proof is kind of in the construction, like the construction markings. Okay? So, question? Yeah, right, exactly, yeah. All right, so let's take a look in our books then, too. Our book has some more practice with this as well. So you guys get your books out, please. On page 359. Okay, 359, please. 359. 359. Oh, no, you're good. I'm sorry. Of course, one thing you have to worry about is when you start getting like on a bigger scale of the planet's not a plane, it's not flat, it's a sphere, so it might not be exactly right. But when you have 3 towns that are like near to each other, that's close enough. You can use, it's close enough to a plane. So, okay. One thing I forgot to mention when I was talking with Alex there, I want to say to you guys too, all right, is that if we talk about 3 cities on a map of the entire United States, we have to be a little more careful about using that the circumcenter construction because, okay, the bigger you kind of work, the bigger kind of area you're working with on a map, all right, what type of shape is the Earth? It's a sphere, right? Yeah, it's round. And so to kind of like to use this, we were working on what kind of shape here? On a flat piece of paper, right? Not 3-dimensional. So we have to be careful. The construction on a map would not be exactly the same. We'd have to like worry about like the curvature of the Earth sometimes, depending on how big you're talking about of a space. But if we're talking about like 3 towns that are near each other, so like I said, Baltimore and Washington are kind of close to each other. And if you want to come up with a 3rd town,
it wouldn't matter because it's like on a piece of paper. It's a map.
right? But understand, a map is not an exact representation of the distances between 2 points. The map is not an exact representation of the distance between 2 points because the Earth is curved, and so when you look at a flat map, it's not an exact representation of what it would be on the Earth. I mean, there's actually like, and I don't know if you guys have ever seen this before. I mean, like sometimes if you have a flat map and you think, oh, the shortest distance between like here and like London, for example, is just to draw a straight line, but actually it's not. It's a curved line because the Earth's curved, and so like the way you would fly. If you wanted to go there, the shortest path would not be a straight line on the map. It would actually be a curved line on the flat map, if that makes sense. So, anyway, something to think about. Pretty crazy. Okay? But thankfully, that's why, we don't have to worry about that right now. Anywho, so if you look here real quick, okay, our book does a nice job of kind of summarizing some stuff here, and we're not going to fill in these blanks or anything like that, but so a circle that contains all the vertices of a polygon. So we circumscribed a triangle, but you can also circumscribe other shapes too, okay? And we might look at that later on in this class. But so a circle that contains all the vertices of a polygon is circumscribed about the polygon. It goes around the outside of the shape there. Okay, it's the triangle here. So here, circle C, we call it circle C because its center is C, is circumscribed about triangle XYZ. Okay? And circle C is called the circumcircle, right? Because it goes around the outside, it's a circle, of the triangle XYZ. The center of the circumcircle is called the circumcenter, okay, of the triangle. So C is both the center of the circle, okay, and it's also the circumcenter of the triangle. Okay? So, there's that. We're going to skip these pieces right here. We'll jump over here. And so if we jump over here to the next page, page 360, okay, it talks about proving the concurrency. We're not going to prove the concurrency, but we are going to talk about this. The word concurrent, okay, so 3 or more lines are concurrent if they intersect at the same point. So remember, 2 lines intersecting to point, no big deal, right? That happens all the time. But if 3 or more lines intersect at a single point, that's more special. We call that concurrent, okay? Concurrent, okay? If they intersect at the same point. And of course, the point of intersection is called the point of concurrency. Like that special point where all 3 or more lines intersect is called the point of concurrency, okay? So, when we do the 3 perpendicular bisectors of a triangle, okay, they all intersect, they all have a point of concurrency called the circumcenter, okay? And like we said earlier, so here you can see we have these perpendicular bisectors drawn. They didn't draw in the construction markings here, but there's that point P, it's the circumcenter, okay? And we said it's equidistance, right? So the distance from P to A is the same as the distance from the circumcenter P here to B, is the same as the circumcenter's distance from P to C there, okay? So those are all equidistant. And again, we're not going to prove that. We're just going to use those properties here to help us. All right, so if we skip over here to the next page, 361, okay, we're told that KZ, LZ, and MZ are the perpendicular bisectors of triangle GHJ. So let's just kind of absorb that here, right? Here's triangle GHJ, okay, big triangle there. KZ, there's KZ. Okay, that's a perpendicular bisector. LZ is also a perpendicular bisector, and MZ is a perpendicular bisector, making point Z what? The circumcenter. That's right. Z is the circumcenter here.
If you don't have a protractor, you just make a 90-degree angle to get the circumcenter?
That is one way to do it. Yeah, you find the midpoint and then you do the right angle there. That's one way to do it. Yeah. Okay, so Z is the circumcenter of triangle GHJ. Since that's the case, since Z is the center there, what distances do we know are going to be equal? So for example, Z to H, segment ZH is going to equal what other distance?
ZG.
Z to G.
And Z to J.
And then Z to J, exactly right. Okay, so ZH, this distance right here, from the circumcenter to the vertex, is the same as the distance from Z to G, circumcenter to the vertex, and the same as the distance from Z to J. So you can even mark those congruent if you want to. They're like that. We know they're going to be congruent. Must be, because it's a circumcenter. All right. So let's see what we can come up with here. So it says given ZM is 7. So here's Z to M. This distance right here is 7. Okay. Z to J. This distance right here is 25. Okay, and H to K, so H to K, this distance right here is 20. Okay, they asked us to find 2 things here, ZH and HG. I can zoom in a little bit better there, I think. Okay, so yeah, Corey?
C to H would be 5, H to G 40.
Okay, so yeah, so Z to H here is 25, right, okay, because again, Z to J is 25, Z to H will be 25, Z to G must be 25 then as well. So yeah, ZH must be 25 there, okay? And then what did you say HG had to be?
40.
How'd you get that? Yeah, don't forget, folks, right? What is K? K, right, is this segment here. KZ is a perpendicular bisector. So this segment is right angle to this side, but also divides the side into 2 equal parts. K is the midpoint. Exactly right, Corey. So if K to H is 20, then G to H, the full distance, must be twice that, or 40. Yeah. So let's see here. I can say GH equals 2 times KH, which is equal to 2 times 20, which is equal to 40. Okay, so there you go. GH is 40, ZH is 25. Okay, using the properties of the triangle here. The fact that HZ, GZ, and ZJ are equidistant, and that KZ, MZ, and LZ are all perpendicular bisectors. Okay, so we're using a lot of properties in there. All right, let's try another one here. Now, the next one here says ZH is 85. So here's ZH. And I use this pen here. That's probably a bad idea for me to do that. Okay, I'll cross those out. So ZH now we're saying is 85. MZ is 13. Okay, and HG is 136. So from H to G, the entire distance here is 136. That whole distance there. Okay? So let's make sure we mark that correctly. So HZ is 85, MZ is 13, and HG is 136. All right, so ZH is the distance we want to, KG is the distance we want to find here. So here's K to G. Okay? What must KG's distance be based on this information? Okay, careful, not 25. That was the old marking. What's the new distance? 13 is from here to here. Does that look like it's going to be the same thing as here? 68? Where'd you get 68 from? Oh, one. This?
28.
Shh. Don't just say things, please. 68. I'm not sure where you're getting 68 from. Oh, okay. So yeah, so KG is, yes, going to be 68. The full distance here is 136. Right, again, K is the midpoint, right? This is the perpendicular bisector that makes K the midpoint, and so if the whole thing is 136, 136 divided by 2 is 68, and that's what KG is going to be. Okay, 68. Okay, ZJ. Well, this distance right here, what about Z to J? What's that got to be? Yeah, 85, okay? If H to Z is 85, G to Z is also going to be 85, and so Z to J will also be 85. Okay? So there it is. Just using those properties there. Okay? Using those properties. Questions on any of that, about where any of those came from or anything like that? All right, if not, I want you to turn the page and try number 5, please. Okay? Turn the page at the your turn there. Read the directions up here. Okay, and I want you to try number 5. Give that one a shot, please. Okay, try number 5. Okay, you're given some information. I'd say label your picture too. Okay, label that picture. Oof. Okay. Just going to look at that picture there.
Number 5.
Number 5, please. Try number 5.
Number 4.
Shh, try number 5, please. Number 5 and try. It's going to be the next one. Okay. I'll be right there.
Wait, what'd you get for DJ?
65. Yep. So H to J. So here's H, and then back to J. So what do you think that? Can you figure that out? Okay, those are talking about degrees though. We're not talking about angle measures. We're talking about side measures. You can't say this way, but distinctly, like we're talking about just right here. No, it should be. I didn't look that way. I understand what you're saying. Why? Because L is a perpendicular bisector. L here is a perpendicular bisector. I know you're right. It's not okay.
I don't like my friends say that I don't
Okay.
Real quick here, folks, let's take a look. Okay? So we're told that ZG, from Z to G here, is 65. Okay? H to L is 63. And then Z to L is 16. So there's the labels, okay? That's what you want. That's what you want to label there. Listen, please. We're told that KZ is perpendicular bisector of that side right there, right? ZL is a perpendicular bisector, and ZM is a perpendicular bisector as well. Okay? So we want to find the length from H to J. Well, if H to L is 63, okay, how can we figure out what H to J is going to be? 63 times 2. Yeah, it's another. Listen up here, folks. We're almost done. So HJ is just 63 times 2, which is 126. Okay? I know it doesn't look like L is in the middle there, but it has to be if ZL is a perpendicular bisector. Okay? So we can say that this is also 63, and so the whole thing then is going to be 126. Last thing here, Z to J. Z to J. Okay, what's this distance have to be? 65, right, okay, so ZJ is 65, okay? Your homework tonight is not going to be very long because I can't let you take the compasses home. So if you'll turn the page to page 366, okay, I want you to try 5, 6, and 7. Notice number 7 says you might need to use the Pythagorean theorem. Remember that's a squared plus b squared equals c squared. So 5, 6, and 7 for homework there. Page 366, 5, 6, and 7.